Imagine two identical clocks, synchronized to the nanosecond. If you separate them and move one across the room, you would expect them to still agree when reunited. Yet, under the right conditions, they will display different times, and both will be absolutely correct. We struggle with this because we treat time as a universal background, a rigid, invisible metronome that ticks at the same rate for every corner of the cosmos. Albert Einstein upended this assumption by focusing on the speed of light. He realized that light in a vacuum travels at a fixed constant of exactly 300 million meters per second, and it refuses to change that speed for anyone. This creates a problem for classical mechanics. Usually, if you throw a ball from a moving car, the speeds combine. But a beam of light fired from a rocket moves at the same speed as a beam fired from a flashlight on the ground. The speeds don't add up.
Einstein realized that if the speed of light cannot change to accommodate the observer's motion, then something else in the equation has to give. He suspected that the variable was time itself. To keep the speed of light constant, time must be a physical property that bends based on how you move through space. It is not a fixed river flowing at one speed, but a flexible dimension. This diagram illustrates a light clock at rest. A single photon bounces between two mirrors placed 1 meter apart. At the speed of light, each round trip takes exactly 6.67 nanoseconds. Now, imagine this clock is on a train moving at 80% the speed of light. To a stationary observer on the platform, the mirrors are moving horizontally, which forces the photon to travel a much longer diagonal path to hit its target. This diagonal trip is 1.67 meters long. Since the photon cannot speed up to cover that extra distance, it simply takes longer to complete the bounce. From the outside perspective, each tick now takes 11.1 nanoseconds. By simply moving the clock, you have physically slowed down the passage of time relative to the world outside the train. This leads to a logical deadlock, the twin paradox. Since motion is relative, the person on the train sees the station moving away from them. To the passenger, it's the person on the platform whose clock should be running slower. Logic alone cannot settle who is right. To prove that time actually dilates, physicists had to move from thought experiments to physical hardware. The first empirical test involved synchronized atomic clocks in commercial airliners. This apparatus represents the precision required for the test. Researchers compared a stationary cesium clock against one flown at 250 meters per second for 10 hours. When reunited, the flying clock lagged behind by exactly 12.5 microseconds, just as predicted. Even more undeniable proof comes from the world of particle physics and a subatomic particle called the muon. Muons, created in our upper atmosphere, have a lifespan of only 2.2 microseconds. Even at nearly the speed of light, they should only travel 660 meters before decaying. They shouldn't even come close to the ground. This chart compares how many muons we should detect at sea level versus how many we actually find. Our detectors are flooded with muons that have successfully traveled over 10 kilometers. This data only makes sense if the muons' internal clocks slow down. Traveling at 99% the speed of light, their time dilates by a factor of 7, extending their lifespan just enough to reach the surface. Remarkably, the muon doesn't feel its time stretching. From its perspective, the Earth's atmosphere physically contracted in length. Space and time are performing a joint balancing act to keep the speed of light constant. Einstein eventually unified these concepts into a single fabric called space-time. In this model, time is not separate from the 3 dimensions of space. They are woven together, and your path through that fabric determines how much time you experience. This isn't just a theoretical curiosity for physicists. It is an operational requirement for the GPS satellites orbiting the planet right now. Orbiting at 3.9 kilometers per second causes satellite clocks to lose 7 microseconds daily, but weaker gravity at that altitude makes them tick 45 microseconds faster. Combined, the clocks drift ahead by 38 microseconds every single day. If we didn't use Einstein's equations to correct for this drift, GPS navigation would accumulate errors of 10 kilometers every day. Within 24 hours, your phone would think you were in a different city. Time dilation functions as a tangible, stretchable dimension of physical reality. We are forced to calculate and engineer around these relativistic shifts, simply to keep our modern world synchronized.